Hello, this video is going to give you a little bit of an introduction to pressure, forces, and wind. This is some interesting stuff that we're going to work on here as we get into the upcoming week, and this is going to give you a little bit of a background and make sure we're in good shape with regard to what are we talking about with atmospheric pressure, again, how do we measure it, correction to sea level, and set us up for some, to be fair, a little bit complex topics such as Coriolis effect that are going to help us to understand why the wind blows the way that it does. And so we're going to have a better understanding of why certain days are windy and why other days are relatively calm. And I've alluded to this a couple times in lecture when we've talked about gradients. And so we're going to talk about things such as pressure gradients and how when for instance, on your lab this week, you saw that when ISO heights well above the surface are close together, that often corresponded with some stronger winds. And so that's going to help us here to understand why is there wind. Understanding what other forces are having an effect on wind speeds as well as directions. Why do winds flow differently around a high in the northern hemisphere versus the southern hemisphere? Why do winds blow in towards a low and out from a high, so on and so forth. How does the pressure affect our weather? In a nutshell, low pressure is usually going to be correlated with some adverse weather, maybe some rain, snow, windy conditions, whereas a bubbly high pressure may be, well, not too far off from the weather that you're experiencing right now, should you be watching this video over the weekend. And so again, got to get into a feel of low versus high, and then, well, is Chicago really the windy city? You may know the answer to why Chicago is called the Windy City. Maybe if I remember on Monday, we'll have a chance to see who watched the videos and maybe knows why it's called the Windy City. Your hint is it is not because it is the windiest city. Far from it, to be honest. Reviewing air pressure, what is atmospheric pressure? We're simply talking about the mass of the air above us at any one point. And so here we got that pressure is a force over an area. Force is that mass of the atmosphere accelerating due to gravity, and so it's going to be highest near sea level and lower as we go up. Again, the one thing you can take to the bank here in MET 103 is that pressure will always decrease with height. We don't have to worry about pressure inversions or anything weird like that. And so what ultimately happens, and you saw this back in lab 2, is that pressure decreases much more rapidly in the vertical than it does in the horizontal, even if there's some pretty significant systems, such as, say, a Hurricane Sally reaching the coast. By the way, we may be talking about another new tropical system down in the Gulf here before we meet on Monday. But what we have here is this idea of wanting to understand differences in pressure on a level playing field. And so we're still going to get back to that correction to mean sea level pressure in order to really compare, say, the weather in Valpo versus the weather in Boulder, Colorado. And so this is another one of those take to the bank things. And if you need a moment or two to kind of give this one some thought, pause and just take a look at the graphic, because it should make some inherent sense. When we talk about pressure, pressure is always going to try to move air from higher pressure to lower pressure. The atmosphere and the weather associated with the atmosphere is basically the atmosphere always trying to get into a sense of balance. It's never able to achieve that balance. Again, the idea that we have warmer weather near the equatorial regions and colder weather towards the poles, that's going to drive this heat transport. It's trying to make everyone on Earth or every location on Earth the same. And it can't. And so if we have an area with high pressure here, your left tank, and we have an area with lower pressure on the right tank, we're going to try and move some of that fluid from the higher to the lower. And that produces a net force that you can see there going from the high to the low. And so later on, not in this video, we're going to talk about the pressure gradient force. And that is always, that's 3 always, going to blow from high to low. How do we measure pressure? We do it with what's known as a barometer. We talked about barometers briefly earlier on when we talked about pressure, but this gives you an idea of pressures that we might experience under some extremes. Again, we measure it in many different units, including inches of mercury, millibars, pascals or hectopascals, and then in this class mainly going to focus on pascals, hectopascals, and remembering that a millibar is equal to a hectopascal. So you're going to be good to go there, which is really nice. Inches of mercury is more used in specialties, maybe some things like reading altimeters for aviation purposes. And so here you can see highest pressures up around 1084 or 32 inches of mercury. Deep high pressures up in Siberia. If you remember the Siberian high in general circulation. Generally, we're going to look at pressure somewhere here in this 1013 range. That's going to be your typical sea level pressure. If we get our mouse over here. And so strong high pressures maybe up around 1040, deep low pressures in 980. So most of the time we're dealing with right around here. And unfortunately, this must not have saved my most recent version. My computer is not playing nicely right now because my Bluetooth won't work. You all definitely needed to know that. But I can see Hurricane Dorian, which was a significant storm last year, came in around 910 millibars. You can see Katrina here at 920. If you remember earlier in the year, Laura, our significant one that hit Louisiana, we were looking at about maybe 935, 937 if I recall. So again, way below what we have on here is your deep low pressure system. Those hurricanes are going to have intense low pressure associated with them. Barometers, maybe we didn't show this earlier. I had a dream that we did. We have multiple things that we could use. We don't have much in terms of mercury barometers. In fact, we had one in our department not long ago that fell, broke, and, well, let's just say that wasn't the most pleasant thing to have to deal with. Mercury is not the safest material going around, but these are what the earlier barometers consisted of, to where mercury being a very dense metal but occurring in liquid at standard temperatures on Earth, pressure down on that mercury would cause this liquid to rise in a vacuum, and so the level of mercury would have some indication of what the air pressure was. We have a number of other ways, such as aneroid barometers. Basically, as pressure moves this little coil, the dial is going to change and help us to tell a little bit in terms of what our pressure is outside. It's important, again, to understand the correction from pressure to sea level pressure. And this is all going back to that idea that Denver is always going to show a big red L for low pressure over the United States if we don't do this correction. And sometimes Denver is under relatively high pressure. And we want to make sure that we're on what we refer to as a level playing field. So again, we know that this pressure decreases with altitude. We are interested often as meteorologists or as lay people trying to understand what's going on with the weather of what changes are occurring near Earth's surface. And so again, I've said it, so the bullet says all that I need to say. We want to be able to do a comparison, and so we get just to sea level. And so in this example, we have areas here, A, maybe around 952, 979 at B, a much lower 894 because we're at a higher elevation, and then 1,000 millibars as you get down to sea level. We do a correction. We did this in the lab. We won't belabor the points, but simply we apply some correction to indicate what would 894 be representative of if it were actually at sea level. And so what you see here is that if we didn't correct, we'd have a big low here, a big high here, maybe another low out here. But once we bring it all down and correct, we can see that we actually would have a high pressure out here near point A, and the lowest pressure would be actually occurring out here near point D, and this would tell us a lot more about what weather conditions to expect. Ultimately, we get a chart with a number of locations being corrected towards sea level. We start to draw lines of equal pressure, and we're going to talk about that with the homework assignment, which has been posted to Blackboard. So if you are reading this and want to get a jump on the homework, you can print out and look at assignment 2. We will talk about it at class on Monday. It deals with isoplething. So if you enjoy drawing some jet streams, you may really enjoy lab or the homework assignment that you have outstanding. We're going to give you plenty of time to work on it, though, about 2.5 weeks on Monday. To get a feel for how to do some isoplething and analysis. Horizontal pressure, again, we deal with this high to low. The basis for looking at these atmospheric pressure differences is going to be related to temperature. The idea that here in this building on the right, warm air is going to expand, cold air is going to contract. And so what that oftentimes means is that we're going to see that expansion, meaning less dense air. That less dense air is going to mean that the pressure may feel low here down at the surface, whereas it's going to be contracted in the vertical, more pressure in a shorter column. And so what happens is that you have more air above a certain level in column 2. Say here as we get away above the surface, that's going to lead towards a high pressure aloft under these warm conditions. And this is relative to a same level here. And this may induce some form of a circulation that occurs. So high pressure Aloft may be associated with low pressure near the surface, and you can start to see that this circulation may feel a little strange in some instances. This air rising in association with the low. Yeah, I get it that you have the low moving towards the high, but if you look in the horizontal plane, we're still going to focus on that high moving towards the low, and here a high moving towards the low. And so what happens is that this air gets forced from high to low pressure, this idea that the atmosphere continues to try to move into some form of a balance. Looking at things here on a plane, which we might see here in some earlier graphics. Similar, we have this warm air column is going to be more expansive, lead towards a higher 500 millibar height. Cold air is going to be more dense, it leads towards a lower 500 millibar height. So again, summertime, we get these deep columns. Here might be in the south as we indicate here. North, much, much cooler and a more dense column. And so that pressure is decreasing more rapidly with height. That's really what you have to kind of think of. We may be at 1,000 millibars at both of these locations, but it decreases to 500 millibars much, much more quickly where it's cold than it does where it's warm. And so that warm air, the expansion, a slower decrease of pressure with height, and this results again in what we refer to a pressure gradient. When we talk about a gradient, we're talking about this change over a distance. And so you're going to induce a pressure gradient here from north to south based upon these differences in pressure, which we see are ultimately related to differences in temperature. These can occur both aloft as well as down near the surface. For the most part here in MET 103, we are going to keep things focused on the surface, but inherently we have to discuss the atmosphere as three-dimensional, because what is occurring at the surface is driven so importantly by what's aloft. And as we're going to see here in this lecture series over the course of the week, sometimes it's actually easier to work with what's going on aloft because we don't have to deal with friction. Friction at the surface can make things a little more difficult to grasp. And so I'll end with this slide. Why not? The idea here of isobars with mean sea level pressure. Here you would see in this example a number of lines that look really squiggly on the left and much, much smoother on the right. This might be the first drawing here on the left, and then we try to smooth things out to make it a little more easy to understand on the right. And so when we draw isobars, iso, same, bars being, well, millibars, a way of expressing pressure. And so we correct these values down to sea level, and then we try to draw where the lines would be equal. We're going to spend a little bit of time on this on class on Monday, so hopefully you've had a chance to review this video and have a little bit of feel of what we're talking about. And so by doing this, taking a whole bunch of these little stations, our station models, and trying to analyze what's going on, we can quickly look at a map and deduce where high and low pressure systems are instead of simply looking at a map that is completely full of numbers. And so this would tell us, hey, there's a low pressure going on across the Rockies. Maybe I'm going to expect some potential for severe weather out in the plains on a day like this. High pressure kind of extending through the eastern Great Lakes. Maybe a little bit of a tighter pressure gradient in areas here across Nebraska and Kansas. So maybe some stronger winds as opposed to some light winds in these areas across the Dakotas or across the Cascades, sort of the northwestern United States. And so we can tell a lot by doing these analyses of sea level pressure. On your lab this past week, we talked about iso heights up at 300 millibars, and those are simply lines of equal height at a given pressure. They are very similar. I think for probably 95% of people, it's a little easier to grasp isobars because we can all understand what it's like to be at sea level and analyze pressure. It's a little different to say, hey, we're going to go to a certain pressure and analyze the heights at that level. But all in all, it's effectively the same thing. All right, still not the longest video. We're going to go ahead and stop it here. Hopefully you have a chance to view these over this beautiful weekend, and we will see you all on Monday. Take care, stay warm.